If you picture the solar system in your head and try to identify Earth's closest neighbor, you probably arrive at a quick answer based on the order of the planets. Earth is the third rock from the Sun. Venus is the second. Because their orbital paths are right next to each other, it makes intuitive sense that Venus is our nearest planetary companion. But run the numbers over time, and the math tells a different story. On average, the planet closest to Earth is actually Mercury. This data visualization tracks the orbital paths of the inner planets. While Venus does get physically closer to Earth than any other planet at its absolute closest approach, it spends the vast majority of its time sweeping far away to the opposite side of the Sun. Mercury, with its tight, compact orbit, consistently stays closer to us on a day-to-day basis. We tend to visualize the solar system as a fixed map. In reality, it operates like a chaotic track field. Planets travel at completely different speeds along elliptical loops, meaning the distance between any two worlds is constantly changing. If you treat the solar system as a static series of rings, the actual mechanics of space travel and cosmic observation remain impossible to grasp. To understand how extreme these shifting distances are, we can look at the math required to reach Mars. This animated diagram compares the minimum and maximum distances between Earth and Mars. When the two planets pass close to each other on the same side of the Sun, they are 54.6 million kilometers apart. But when they end up on completely opposite sides of the Sun, that distance balloons to 401 million kilometers. Even the massive gas giants are subject to this elastic geometry. In 2021, Jupiter reached opposition, an astronomical event where Earth passes directly between the Sun and a distant planet, putting Jupiter at its absolute closest approach to Earth, nearly 600 million kilometers away. At this scale, tracking planetary motion in standard kilometers creates numbers so large they lose their practical meaning. Astronomers solve this by using the astronomical unit, or AU. 1 AU is exactly the average distance from the Earth to the Sun, about 150 million kilometers. Human measurements designed for roads and cities break down in the void. We have to use the physical dimensions of the solar system itself as our baseline yardstick. Because everything is orbiting at different speeds, engineers face a massive mechanical challenge. You cannot launch a rocket in a straight line toward your target. By the time you get there, the planet will be gone. This orbital map traces a Hohmann transfer orbit, an elliptical trajectory moving a spacecraft between circular orbits using minimal fuel. To execute this, engineers wait for a precise Earth-Mars alignment. The spacecraft launches into the void, curving outward to intercept Mars months later. The Hohmann transfer is elegant, but for targets at the extreme edge of the solar system, elegance gives way to raw physics. When NASA launched the New Horizons probe to Pluto, the spacecraft had to travel at 58,000 kilometers per hour. Even at that speed, the journey took 9.5 years. To cover that immense distance, New Horizons had to thread the needle past Jupiter, stealing a fraction of the gas giant's orbital momentum in a gravity assist to slingshot itself deeper into the outer solar system. Navigating the solar system requires aiming at empty space, calculating exactly where a world will be years in the future, and trusting the math to catch it. Moving across these massive distances reveals an even stricter boundary in physics. Light travels at roughly 300,000 kilometers per second, the absolute speed limit of the universe. Yet the void of space is so large that even light struggles to cross it instantly. This delay forces us to upgrade our ruler one final time, to the light year, the distance a photon travels in 1 Earth year. It functions as a measure of extreme scale, but it also acts as a direct measure of time. When you feel the warmth of the sun on your skin, you are interacting with energy that was emitted 8 minutes and 20 seconds ago. That photon had to cross 150 million kilometers of vacuum before it finally reached Earth. Every interaction carries a delay. The light coming from the screen you are looking at right now is a few nanoseconds old. The light reflecting off the craters of the moon takes a full second to reach your eyes. Because light has a finite speed, viewing objects across massive distances means you are literally observing them as they existed in the past. Look up at Alpha Centauri, the nearest star system to our own, and you are seeing light that has traveled for over 4 years. If that star were to suddenly vanish, we would not know about it until 4 years from now. Push that scale to the extreme. The spiral galaxy M109 sits roughly 83 million light-years away from our solar system. Imagine an alien civilization in M109 has built a telescope powerful enough to zoom in and look at the surface of Earth right now. Because the light bouncing off our planet takes 83 million years to cross the void and reach their lenses, they would not see human cities. They would see dinosaurs walking across a prehistoric landscape. When you stand outside at night and look up, you are taking in a mosaic of different eras. The night sky is a catalog of moving targets, separated by shifting voids, where every point of light is a window into a different moment in history. You are looking at an ultimate cosmic time machine.